Hey everyone, let's talk about rotation and translation that are happening at the same time. So if we do that, we need a few things first to understand an object that is rotating and translating at the same time. And by rotating and translating, I mean, let's imagine a wheel that is turning, but that is also moving forwards as it turns. So let's say it's rolling on the ground. If you pick a point on that object, like right here, that point has a velocity due to the rotation, and it also has a velocity due to the wheel moving forwards. And that point's net velocity is the sum of those two velocity vectors. So due to rotation, its velocity vector might look something like that. And due to moving forwards, its velocity vector might look something like that. And the net velocity of that one point is actually the sum of these two vectors, which would look something like this. So that would be the net. That would be due to rotation, and that would be due to translation. So you can do that for every single point on this body and figure out what the net velocity vector would look like for each point. That's what rotation and translation means for the velocities of the points on an object. But before we do all that, we need some relationships that we may have seen before, but that you may have forgotten. The first one is this V equals R omega relation, which is extremely useful when you're dealing with bodies that are rotating and translating at the same time. And it needs a little bit more explaining. It's a little misleading the way that it's written just in general right here. So imagine an object that is rotating only. It's fixed in place around on some axis in the middle. So this is just rotating. If you pick a point on the edge, and let's say that this object has a radius of capital R. If we pick this point P on the edge and we follow that point through one full rotation, the time for that rotation happens in, let's say, t seconds. So the time period is capital T. And if it has an angular velocity of omega, we could say that omega is 2 pi radians divided by t seconds, because it turned a full circle in t seconds. So the angular velocity would be 2 pi over t. And if you remember from circular motion, this itself is one of the relations. That's the relation between time period and angular velocity. But here we are using it to prove this equation over here. So if this object is only rotating, then point P will have one velocity. Its velocity at this instant, as drawn, its velocity will be to the right. And that is perpendicular to this line connecting it to the center. That velocity is often called tangential velocity. So that is tangential velocity. I don't think IB actually calls it this, but it's a little misleading not to label it with this label, tangential velocity, because when this object, let's say instead of just rotating, if this were rolling, point P would also have another velocity associated with it. And that's why we need a specific name for velocity due to rotation, and that is often tangential velocity. The reason it's called tangential velocity is because if you draw a line connecting whatever point you're looking at to the center of rotation, the velocity due to rotation will always be tangential to that line. So it's called tangential velocity. So even on an object that's not a nice circle, let's say this weird shape up here is rotating around that x. If you pick any random point, the path of that point due to the rotation ends up being a circle around x. And so right now, as drawn, the velocity would be tangential, even though this is not a circle. So the word tangential works even for objects that aren't nice and circular. Okay, so the tangential velocity, let's say vt, that's tangential velocity. We could calculate that. If everything was nice and uniform and it wasn't speeding up or slowing down, we could calculate this by figuring out how far point P goes linearly in one full time period. So we need some distance on top divided by t. So distance over time. The distance on top that it goes in one full time period is just the circumference of the circle that it's traveling in, 2 pi capital R. Now this works even if the object is not a circle, like I just showed you, and it also works even if point P is not at the edge of the object. If point P were really somewhere down here, instead of plugging in the radius of the object, you would just plug in whatever this distance is up to the point you're looking at. So R in this equation is the distance from axis of rotation to the point you are interested in knowing the tangential velocity. So it doesn't have to be a point on the edge of the object. If it is on the edge of the object, then you plug in the radius of the object, which is what I've done here. So if you compare these two equations, 2 pi over t, 2 pi over t, that's in this equation. So I can replace 2 pi over t with omega, and I get tangential velocity of point P equals the angular velocity of the object times the distance between the axis of rotation and the point. So in this equation that I just derived, r is the radius of the object, but r doesn't have to be the radius of the object, because if the point that we were interested in wasn't on the edge, you would just use whatever distance you needed, not the radius of the object. So this equation is very useful, but it should be, I think, called tangential velocity, and it should be clear that this tells you the velocity of a point on a body. Well, it tells you the tangential velocity on a body due to its rotation. Now I think it's a much more useful formula because you know the limitations on it. All right. Next we need to talk about moment of inertia before we can really fully explain an object rolling on the ground. And moment of inertia is one of those topics which you kind of need calculus to fully grasp, or at least to fully do mathematically. I think you can understand moment of inertia without the calculus, but if you don't have the calculus to do integrals, then you don't really understand where the formulas come from. So I'll get to the point where you would do an integral, and then I'll say, here's the answer. If you read the textbook readings that were assigned, the way that Sokos introduces moment of inertia is, I think, kind of a good way, for a textbook at least. The best way to do this would be is if we were all in the same place and I could roll some things down an incline for you, which I can't do. Instead, pause the video after I give you this link. Find the link, watch that video, and then come back. Okay, you should have watched that video, now you're back, and you saw in that video that a hoop which had no material on the inside and all of the material was at a certain radius versus that was the ring. The ring has all the material on the outside, and then the solid cylinder of wood, they had a race down an incline. And they were made of the same mass, so our old physics would have predicted that they reached the bottom at the same time. Well, actually, our old physics, delete this part, delete this part, delete this part. So they reach the bottom at different times, even though they have the same mass, because that mass is distributed differently. If you look on this chart, that was basically a race of these two versus each other. And if you look at the moment of inertia for them, one of them has half the moment of inertia of the other one, if they have the same mass and the same radius. So the one whose moment of inertia is smaller has less resistance to rotation, therefore it gets rotating faster when the same torque is applied to it. And when we do the full math of rolling, you'll see why I leads to a larger acceleration. But for now, we're still just talking about moment of inertia. So in SOCOS, they show you an object. Let's say this thing is rotating around that point X, and you pick a few different points on the object and look at the kinetic energy of, let's imagine that at each of those points it's a chunk. We cut out a chunk of mass. Call that M1, M2. It's a tiny chunk, so that the location is pretty well defined. M1, so that's R1, that's R2, R3. These are the distances between the chunk of the object and the axis of rotation. Well, if you keep cutting the object in chunks, what you'll get is a bunch of chunks of mass that are moving. Each of these chunks has a tangential velocity, which is perpendicular to that line connecting them to the center. They each have a tangential velocity, v1, v2, v3, dot, dot, dot. And so if I want to calculate the kinetic energy of rotation, which of course this thing better have kinetic energy if it's moving, if it's rotating, because even though we haven't looked at or done this yet, how could it not have kinetic energy? It's spinning. Something had to give it energy to start spinning, so it better have energy, and that type of energy is called rotational kinetic energy. So EK would be 1/2 times the chunk 1, 1/2 mass v squared, plus 1/2 m2 v2 squared, plus 1/2 m3 v3 squared, and you just keep doing this, dot, 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 until you get the entire object cut up into chunks. So what that would look like, let's say I cut it into n chunks, however many chunks it takes, n, and I do a sum from I equals 1 to n of 1/2 mi vi squared. This term would be the kinetic energy of that whole object. If you did the cutting right and you measured the masses of the chunks right and you measured the velocities of those chunks correctly, and you cut it up so that you got all of the object, that would give you the kinetic energy of the object. But that's a pretty useless formula, because you can't really go cut up an object into that many tiny chunks and measure all those things. So let's use V equals R omega, V tangential equals R omega, to replace the VI here with R and omega. This whole object, let's say, has rotational velocity omega. So the formula would then become EK equals the sum from I equals 1 to n of 1/2 times mi times Ri times omega, all that squared. And I'm going to pull this 1/2 out front. If you haven't played with summations like this before, then maybe that's confusing, but the summation symbol is just a fancy way of writing this term plus that term plus that term. But look, all of these terms have 1/2 in them. And so instead of putting the 1/2 on the inside, I can just put it on the outside. It's like factoring out the 1/2. All right, So there's the summation symbol. Then here is mi times ri squared times omega squared. This is the kinetic energy of rotation due to an object in terms of angular velocity. And when you look at it in terms of angular velocity, this pops up. It's the mass, but it's also where the mass is, and that location is squared. So if you call that, let's just call it I. Actually, it's the whole thing. If you call the sum right here, because omega doesn't change. Omega is the same for every point because it's one rigid body rotating, so they all have the same angular velocity. If you call this whole sum I, then I can write this formula 1/2 times I times omega squared and put a box around it. Remember that that's rotational. The translational version, or linear, was 1/2 times mass times velocity squared. So it looks like I seems like m when you compare these two formulas, because there's a 1/2, there's a constant, and then there's a velocity. And in fact, I is like m. I actually involves m, but it involves more than just m. It involves m and where the m is. So in doing this sum, if the location of each little chunk is farther away from the axis of rotation, then the Ri values will be large. And you'll end up with a larger value for the sum, and you'll end up with a larger value for I. If instead, when you're doing this sum and the Ri values are all kind of small, that means the majority of the mass is located closer to the axis of rotation. That means I will be smaller. And you should think of I as I is resistance to angular acceleration. So if you're trying to spin something and spin it faster or slow it down from spinning, the thing that resists that is I. Just like if you're trying to push a box across the room, that box's inertia comes from its mass. Well, rotational inertia is the same thing as what we call moment of inertia. I like the term rotational inertia much better because it's more modern, and when you learn physics these days, the idea of moments don't really even come up anymore. A moment is sort of an outdated term which kind of is the same thing as a torque. And so if you know the meaning of the word moment, then moment of inertia makes it kind of make sense, but it only makes sense if you know the meaning of the word moment. But we don't teach you what that is anymore, so I don't like the term moment of inertia, but everyone still calls, a lot of people still call it that. Rotational inertia is a much better term. If you say rotational inertia, everyone will know what you're talking about. If you say moment of inertia, everyone will know what you're talking about, but it's easier, I think, to understand rotational inertia. Okay, great. We see that in this derivation of rotational kinetic energy, I found a sum which has m and r squared in it, and I called that sum I. So where do all these formulas come from? Well, they come from doing that sum for these different shapes. And in practice, when you do this sum, you don't really cut a chunk, measure it, and then add another term. Instead, what you do is an integral. So the sum from I equals 1 to n of mi ri squared becomes an integral of r squared, where mass is the differential element. And If this discussion of the integral sounds like complete nonsense to you, that's fine. They're not going to ask you about this integral. They don't even actually expect you to know any of these formulas. The only formula they expect you to know is this one, mr squared. The moment of inertia of a point mass is mr squared. That's the only moment of inertia formula they will ever ask you about, which is the rotational inertia of a point mass, which is rotating around some axis. So if this is the axis and you have a ball that's rotating in a circle around that axis, its moment of, and it's r away and its mass is m, that moment of inertia of that ball relative to that axis is mr squared. That's the only moment of inertia IB expects you to have memorized. And it might even be on the data booklet. Okay, get rid of that. I was explaining how the sum turns into these formulas in practice. And what you do is you integrate over the entire object. The dm is the tiny chunk of mass, and the integral is summing all the tiny chunks of mass. And in practice, dm, which is, remember, that's a tiny chunk. A better way to calculate the integral is to say, well, if the thing's density is rho, and I multiply by instead a differential volume, then rho times the differential volume is the differential mass. So you don't actually do it in terms of mass, you do it in terms of volume. And volume integrals are what are known as triple integrals. So a simple one might look like dx, dy, dz, and this looks complicated, but it's really just one integral followed by another integral followed by another integral, and the result of each one gets multiplied by the other integrals. So they're not really that complicated to understand. They're complicated to do. They're not complicated to understand the function of them, though. And so this is the point where I'm going to stop and say, you'll learn this later if you need it in college. These integrals, to come up with these shapes, aren't all that hard, and you know all the math that is needed to do them right now. It's just learning how the integrals work. If you've taken either of the AP calculuses, then you've already done, or you will do, integrals like what you need to do to get these. You just may not have done double integrals or triple integrals. All right, this video is getting pretty long, so I'm going to end it here. Don't forget to like and subscribe, and sign up for the competition where there's a giveaway. I don't know. I'm not a YouTuber. The end.